Hello, welcome everyone. It'd be great to hear from you in the chat. I hope you're having a good weekend. Feel free to send any messages through. I know we're in May now, it's gone really quickly this year and we're already in the kind of exam season. So we've got a good session prepared on chain rule and differentiation. So it's very much a pure maths topic today. But it'd be great to hear from you in the chat. Any questions and answers that you want to share as we go. I'll keep an eye on that. And so welcome if you're just joining. I'll give it a minute or so before we start, but well done to all of those taking part on a Sunday. I know it's probably a big week for a lot of you if your exams are just sort of kicking off this week. So welcome, thank you for joining. Do feel free to say hello in the chat if you haven't already, and I'm going to try and keep an eye on that throughout. So yeah, as I said, we're going to be doing a pure maths topic today. We're going to look at the chain rule, look at some exam questions and so on as well, and work through that. Hi, welcome. Do also let me know if this is a topic you've done before and if this is revision or if this is kind of new to you as well. So it's very much a kind of normally year 13 part of the pure course, and it's part of calculus, differentiation. So I'm going to share the screen and we'll get started pretty much straight away. Hopefully everyone can see the slides just about sharing now. And yeah, we'll make a start. So welcome everyone. We're going to be looking at the chain rule for differentiation today. And there's a sort of series of questions, examples, and we're going to kind of talk through the idea fully with this topic. So do let me know if you've done it before. Let me know if it's revision, and it will give me an idea. But do feel free to, as I said, share answers and questions as we go. Welcome if you're just joining. It's great to see people taking part on a Sunday doing some difficult maths, especially as I know your exams are sort of starting up. Brilliant. Okay, thank you, Casey, and anyone else that's sort of sending messages in. This is maybe something we're familiar with. That's great. Okay, so I'm Max. I've been teaching maths now for the past sort of 5-6 years to A-level, GCSE and below, and been doing classes for Snap Revise over that time. So it's been an interesting time to teach the course as it's changed a bit as well. And we've had to sort of stay very focused on the content that's new and really paying attention to how the exams have changed. This topic's a great one to do. All right, excellent. Thank you for the comments as well. This is quite an involved topic. It's quite far into the differentiation, as I'm sure you're all aware. What we're going to look at to start with, we're going to build this up. We'll look at devising a method for differentiating powers of brackets, which is a sort of very standard way of using the chain rule. Then we'll extend it to negative and fractional powers. Excellent, thank you, Sophie. And then what we'll do is we'll use it to involve trigonometry and also exponential functions. We're not going to cover differentiation from first principles or graph sketching. This is very much sort of a build-up of chain rule practice. Oh, wow, okay. Okay, and good luck with that, Casey. So it's a big week for a lot of people, I'm sure. But hopefully this will be useful. Yeah, excellent. So just as a very much like quick recap of things we should know sort of from year 12 and earlier on in differentiation, differentiating something like n to the power of x to the power of n, we drop the power by 1 times by the power and drop the power by 1. And likewise, we can extend that if there's some constants in there as well. So sometimes it looks more confusing than it actually is when it's sort of fully algebraic, but this is all sort of stuff we should know, and with numbers should be fine. So just be careful with differentiation when there's roots, when there's 1 over, any sort of reciprocals, to change it as powers first. So this is really asking us to differentiate x to the power of 1 over n plus x to the power of minus m. And so that would differentiate to 1 over n, x to whatever that is, minus 1, minus 1 over x to the m plus 1, or x to the minus m minus 1. Cool. Does anyone know what this differentiates to? So just a quick basic recap of what exponentials differentiate to, and what trig functions like sine and cos differentiate to, sine and cosine, what do they differentiate to? So let me know in the chat, e to the x, how does that differentiate? Or a e to the x, a number times e to the x. The derivative of a e to the x. And I know it can be tricky to write into a chat, but a, excellent question, Casey. Yeah, a is just a constant. Let's pretend a is just a number. Then a e to the x, as if it was like 5e to the x, that would just differentiate. Hopefully we're happy to a e to the x. Okay, brilliant. So if it had been a e to the x squared, we would have 2x come down, and that's what we're going to see in the chain rule today. So basically, e to the x just goes to itself. But from the question or the answer in the chat there, we're going to see some similar things to that in a minute. So we are thinking on the right lines, but e to the x as a sort of bog standard thing will just go to e to the x. So if you times it by a number, that differentiates to itself as well. Now, a sine x or sine x differentiates to cosine of x. So a sine x will differentiate to a cos x. And cos differentiates to minus sine. So this one will be minus a sine x. Okay, feel free to screenshot, feel free to ask any questions. This was just very much like a prerequisite thing. We're going to get straight into the chain rule now. I'm going to start looking at brackets and powers and build it up. So please ask me if you need anything clarified or if you want to share answers as well. Brilliant. Right, I'm going to move this on. So this topic is crucial. Whatever exam board you're doing your A-levels with, OCR, EdXL, AQA, the chain rule is a crucial part of the differentiation. So we're going to start by looking at it in the context of brackets and just sort of taking this back to what we might have seen earlier in the course. If you were to differentiate something like this, for a bracket where it's to the power of 2, you might as well open it up, expand it, and just do it the old-fashioned way. But we're going to notice something here, and I'm going to make a link to the chain rule. So who could tell me what x squared plus 6x plus 9 would just straightforward differentiate to? If I were to expand that before I differentiated it, how would this thing differentiate? Because this is a question you could do using the chain rule or not. Brilliant. Thank you, Casey. That looks great. That would go to 2x plus 6, and hopefully everyone agrees. So you times by the power. Excellent, Sophie. Drop the power by 1. Now, what I just want to say for this one is that could, of course, also be written as 2 lots of x plus 3. So notice what's kind of happened if I factorize the answer is it's like the original thing, and I've times by the 2, drop the power by 1, and then the derivative of the inside is just 1. So this is actually the chain rule as well. But because it was just 2 brackets, it was easier just to expand it maybe and then differentiate it. But it does link to the chain rule. And I'm showing you that if you factorize it, you can see there is a link there to what we're going to discover for the chain rule. Likewise, this next one, if I were to open this triple bracket up, which is a little bit more tedious, so I'm going to help you out. If we were to expand the 3 brackets here, it's quite involved, this one. You have x to the 6 minus 6x to the 4. And I'm just doing it really quickly. If you sort of times the 2 out and then times them by the 3rd one and tidy it up. And if you differentiated this, you'd get 6x to the 5 minus 24x to the 3 plus 24x, and then minus 8 differentiated would go. And what this is actually the same as is like 3 times x to the 4, oh, sorry, x squared minus 2 squared times 2x. That's what it's the same as. You could factorize this in this way. And notice it's like the power has come down, and then with times by the derivative of the inside. So in general, what we're saying, the chain rule for this sort of situation is that you can differentiate around the function, drop the power by 1, and then times it by the derivative of the inside. Does everyone recognize that, or does anyone recognize that as a thing? Because this is one of the more basic versions of the chain rule. We will define the chain rule carefully in a second. But if you've got like a bracket function of x, a function of x to a power, you can kind of differentiate around that function. So like drop the power, times by the power, drop the power by 1, and then times by the derivative of the inside. And that would also have worked here. That would be equivalent to the answer if you'd done it the long way. So we will clarify this, but this is sort of one application of the chain rule. So the chain rule is for dealing with functions within functions. So for example, like this is a linear function squared. That's like a function in another function. This is like a quadratic function in a cubic. So what we've done is we've taken the 3 down, dropped the power to 2, and then times by the derivative of the quadratic function, which was 2x. So hopefully that makes sense, but please do ask any questions if you're still unsure, because we're going to do some slightly more involved examples of this and then build it up beyond just differentiating brackets. So the way we're going to do it for this one, and we can work through this first one together, is that this is a function in here. This is like the inside function, f of x, or f of x here, and then it's to the power of 2. So basically what we're going to do is we're going to think, if that's f of x, could anyone tell me what the derivative of the inside function is? What's the derivative of cos x plus e to the x? Who knows what the derivative of that is? So f of x is cos x plus e to the x. What would its derivative be? Great answer. So this would be, so cos would actually differentiate to minus sine x. Well done. Brilliant. Thanks, guys. Excellent answers in the chat. Because we've stepped it up a level now. Minus sine x plus e to the x is the derivative of the inner bit. Good. So to do the chain rule here, the 2 is going to come down the front, like sort of the classic year 12 differentiation, and you're going to get the 2. Then you're going to get the function that was there, cos x plus e to the x, now to the 1. So we've sort of done differentiation on the overall situation, something squared, the 2 comes down, the power drops to 1. And then I times that by the derivative of the inside, which you guys have just told me was minus sine x plus e to the x. And that is actually the answer. You don't even need that 1 there necessarily. This is your derivative. And some people go, oh, do I need to then expand that out? It's actually better having it all factorized, because anything they're going to ask you to do is probably better if it's factorized anyway. So that's what's really good about the chain rule. It also gives you the answer in a factorized format. So what we're going to do is we're going to do the same thing over here. And again, feel free to work ahead of me. These are getting kind of trickier as we go now. And then we'll look at, again, further more complicated versions and some exam questions as well. So this one here, if I just think about the inside function actually as x to the half minus x to the minus 1. Okay, so overarching scenario, it's something to the 3. So it's going to be 3 lots of that thing minus 1 over x to the 2. And now I need to times that by the derivative of the inside bit. So if I differentiate this, I'm going to get, for this one, a half x to the minus a half. So the derivative of that would be a half x to the minus a half. And then that bit would be plus 1 over x squared, or x to the minus 2. Okay, and you can even rewrite that as 1 over 2 root x plus 1 over x squared. And that would be the derivative. So the first bit was actually hopefully quite easy. It was ultimately, we've got a cubic. How do I differentiate that? The 3 comes down, the power drops to 2. Then I times by the sort of internal mechanism, the derivative of that inside bit, which was actually a little bit more difficult. It's a little bit harder. And you can use the index form to help you differentiate that sort of year 12 style if you prefer. Well done. We're going to do a couple more tricky ones now. And then we'll do some exam style questions and push on beyond just this style of chain rule. So well done. Please do ask me though if you need anything clarified, and thank you so much for already sharing suggestions and answers in the chat. Here we go. So same thing again, except this time it might not be as obvious that this is necessarily a chain rule. So what I'm actually going to do, I'm going to do the chain rule on each bit. I'm going to treat each of them as a chain. So sec x, you might already know how that differentiates, but I'm going to show you how to differentiate it by the chain rule. I'm going to treat this as cos x to the -1. Does everyone recognize that sec x is 1 over cos x? So it's like cos x all to the -1. Have we seen that before? That's what sec x, the reciprocal function of cosine. So it's 1 over cos. So it's like cos x to the power of -1. Super, brilliant, guys. So that's how we can sort of employ the chain rule to help us with that. Now this one, I can think of as e to the x to the half. So we can sort of see it as a chain as well. Now the way to do this first one, if I differentiate around the cos, I get minus cos x to the -2 times the derivative of cos x, which is minus sine x. I'll tidy that up in a minute. And then this one, the half comes down, e to the x -1 from that to the -half, times the derivative of the inside, e to the x. Now, if we tidy all of that up, the minus times the minus sign becomes sine x, and the cos x to the -2 is over cos squared x. That can be further tidied up, actually. And then this one would be half e to the -half x times e to the x. You add the powers, and you get half e to the half x. Now, this actually tidies up a bit further. At this stage, you've actually differentiated it. You've done the differentiation. You've done the chain rule. Sin x over cos squared x. Push. Does anyone know what that can be tidied up to? I think it is actually in your formula book as well, the derivative of sec x. But sin x over cos squared x is like sin x times sine over cos. Brilliant. Yeah. So this becomes tan x sec x or sec x tan x. That's another way of writing it. Really well done. That's great to see kind of good confidence moving between the different trig functions there. And then this one could be written as well if you wanted as half root e to the x. Sorry, that should be a half x up there. Well done. Let me go back to the red pen. Right, we've almost pushed through this first bit, and then we're going to get on to some harder exam style questions. Let's just do one more example here so that we can treat this as one single, really more obvious chain rule. And think about how you would perhaps rewrite this, because that could catch a lot of people off guard if they saw that in the exam. So this is actually a chain rule. A lot of people think of it as, oh no, it's quotient rule or something because of the fraction. Because it's just 1 over, we can treat it as a chain, and we can actually treat it as this. Do we all agree with that? So 1 over the cube root of this function is like that function to the power of -1/3. That sorts out the whole 1 over the cube root aspect, and that sort of becomes the outside function. So now I can just differentiate around that using the chain rule. So I'm going to times by the power, -1/3, drop the power of that bracket by 1. So I end up with -4/3, and then multiply it by the derivative of the inside of this. And the derivative of the inside of this would be 3x squared minus 4. And that's it. That's my answer, all factorized. and arguably wasn't too difficult following that process. So what we'll do a quick checkpoint, a couple of exam questions, and then we'll push on to some harder applications of the chain rule as well, and get a much clearer, solid, maybe definition of what it is. But really, really well done, and thank you so much already to all of you that are sharing answers and suggestions in the chat. So here we go, guys. If you could just give me a quick indication, whether you've been sharing answers or not, just to give me a kind of idea how confident we're feeling, a 1, 2, or a 3, in terms of if you're finding this okay, if it's really easy or if it's quite difficult, just to give me a sense of how we feel. Brilliant. And actually looking at your answers and the suggestions there, we seem quite secure in our knowledge of what the chain rule is. But of course, if there's anyone that does want me to explain anything or just wants to kind of indicate it's tricky, feel free. Okay, excellent. So we're going to push on. We'll do a couple of quick exam questions here. This one here, so it says find the value of dy dx, so it's saying to differentiate at the point where x equals 2 on the curve with this equation. Now, this is actually something that a lot of the calculators now, you can get the answer just typing it in, but for a big number of marks, they're going to expect to see the working anyway, but at least some of us can check this quite confidently. Brilliant. So for this one here, and thank you again to all those writing in the chat. So let's rewrite this as y equals. Now, some people think this is actually a product and a chain rule. That's how I probably would have done it. I want to show you a really sneaky way that you could just do this as a chain rule. Can anyone think how we could do it as just a single chain rule and put it as one single square root? Any ideas for this one? What we could do, and this is something that I probably wouldn't spot to do. Yes, absolutely. We're going to use the power of a half to represent the square root, but it's a bit annoying that there's an x squared on the outside. Is everyone happy that technically this is also the same as the square root of 5x to the 5 minus x to the 4? Because this could make this a lot easier. Like, if you think about it, technically, no, don't worry if that's a bit weird. I'm going to, because I would never have seen to do this myself when I first did it. I'm going to show you now. Just to make this an easier question, x squared is actually the square root of x to the 4. Now, you don't have to do this question this way. Some people are confident doing the product and the chain rule together. But can you guys see that if we put x squared as the square root of something like x to the 4, because of rules of surds, you can merge it into one square root. So this is actually the same as, and don't worry if you're sitting there thinking, I would have never seen you to do that, but I've got another way I can do it. That's fine. Do it that way if you want to check we get the same answer. I just think it's actually a lot easier in hindsight that this can be done as one single chain. So does everyone see that that is actually equivalent? And this isn't even a differentiation skill. This is such a random sidestep as well. But it allows us to just do it as a single chain. Does that make sense? If you could clarify for me, guys, that does actually make sense, that that's the same, even if you're still thinking, I wouldn't have spotted to do it that way necessarily. Yeah, but we can see that doing that, yeah, looking out for stuff like that, which you can't always do, but could actually make doing something weird and trickier, could make the differentiation easier. So now what we can do is we can do this as quite an easy chain. Yes, you could also do it another way. You could just do the chain rule on that and then x squared and do the product, but then you'd have to tidy it up and it wouldn't be sort of fully factorized, but it would work. So you have to do the chain and a product, which we're going to look at later as well. But what I'm saying is, if possible, we might just want to do stuff as one single chain rule. So then we don't have to be paying attention to two different rules. But yeah, of course, you could absolutely do it another way, and it wouldn't be too much more difficult. But let's think, this is what we're doing now. And had it been written this way, I think we'd be kind of a lot happier if it was just written like that at the start. If we now differentiate that, guys, check you agree with me, we would get a half minus half. That's okay, I'll explain that in a minute. It is a bit of a random step, so don't worry. If you think I wouldn't have done it, you wouldn't have personally done it that way. But I'll explain that in a minute. That is actually your answer, and then you let x equal 2. You plug that in, and I believe what we get out is 46/3. You plug that in. You can actually type this whole thing into your calculator and check that. For those of you that have maybe the class whiz, you can type it in the derivative function and put x equals 2, and it subs it in and differentiates it for you. Literally type the question in like that in the dy dx button bit. The reason, just in answer to that question of why I wrote it as the root of x to the 4, is so that it was all under 1 square root, which is like the power of a half. So I can just do a single chain rule to it. Because here, this is a chain rule in itself, because it's like 5x minus 1 to the half, and this is x squared. So you'd have to do the chain rule to that, and remember that there's a product rule going on as well. So what we've done is this bit you don't understand, like how root x to the 4 is x squared. Oh yeah. Yeah. You try and sort of show it fully, looking at the number of marks for the questions. That's an absolute, fair point. But I'm just saying, as a checking mechanism, you can use your calculator. So yeah, in answer to if that's still, if we're still a bit unsure, this was a bit of a weird one. So we'll look at other ways you could have done it later as we get onto the product and chain rule mixture. I think that in the same way, I wouldn't have originally seen that you could necessarily want to merge it, but actually it is really helpful, because if there's a number or a squared term or a thing on the outside of the square root, you can absorb that into the square root by squaring it. It's just a helpful technique to know. So if you haven't seen that before, so this is one of the key bits for differentiation for second year: chain rule, product rule, quotient rule, but there's a lot more as well. So we're going to try and get through as much of that as we can. What I might do here is whiz on for this one, because I am conscious of the time and I want to get onto some slightly harder ones. This first question here, this is actually sort of like expressing it as a single fraction that cancels down. I might let you guys try this in your own time, because I'm worried we'll run out of time doing this. And I want to get on to actually differentiating it. But that's ultimately what it simplifies to. So if you did want to screenshot this and then work towards that, all it wants you to do is do a common denominator and then factorize it and cancel down, and it boils down to this. So I'll give you the answer to this first bit so that we can get on and actually differentiate it. Then we're going to push on to some harder chain rule questions. So here we go. So the follow-up to that, so those of you that have done the early chapters of pure in second year will realize there's a lot of algebra, partial fractions, all that sort of thing. And then that comes back again with a vengeance in the differentiation. So here, it now says, show that this can be written in this way. Well, we now know that that first bit can be replaced with our answer to part A. So we end up with 4x plus 1, 2x minus 1 replaces that, and then we're minusing 2. So this is again more playing around with fractions. And then this boils down to 4x plus 1 minus 2 lots of 2x minus 1 all over 2x minus 1. And that tidies up to 3 over 2x minus 1. So it's another show that. So there's a lot of marks in this question that are just actually playing around with algebraic fractions. It's actually part C that says hence differentiate it and sub in a value. So here, how does this relate to the chain rule? Well, let's think of this function. And again, look at how the questions are designed, guys. If you messed up the algebra or you were taking too long with partial fractions, you can still do this part of the question, even if you haven't got the earlier bits. So it tells you this is the function. Now differentiate it. Let's think of 3 over 2x minus 1 as 3 lots of 2x minus 1 to the minus 1. If you now use the chain rule on that, which feel free to work ahead of me and do so, we would get the derivative as being equal to minus 3 lots of 2x minus 1 to the minus 2 times by the derivative of the inside, which is 2. So that comes out as minus 6 over 2x minus 1 squared. And then they've asked us to sub 2 in to that. So that would be when x equals 2, f dash x equals minus 6 over 4 minus 1 squared. So minus 6 over 9, so minus 2/3. And again, it's one you could do and check on your calculator. Right, let's keep pushing on. So this is now sort of consolidating and looking at more broadly the chain rule and the definition for it, and bringing in some of the harder stuff from year 13, the trig functions and so on. So here, just clarifying ultimately what the chain rule is. We just looked at like something to a power. It's actually for functions within functions. So it's actually for composite functions. I'm just looking at the chat. Do you know how? Okay. Yes, good question. So technically, Casey, with the chain rule and the product rule, you can do any question with just them. The quotient rule is sort of a mixture of the chain and product. You could get by with just the chain and product rule. But the good thing is the quotient rule keeps it all factorized as well for you in the denominator and potentially allows you to simplify the fraction. If it's a function over a function, that's generally when you'd use the quotient rule. If it's just a number over a function, then it's sometimes a lot easier just to use the chain rule. Because if it was like 3 over some complicated thing, you could just write it as 3 of this thing to the minus, and then it doesn't need to be a quotient. So the quotient rule is more for functions over functions, as opposed to numbers over functions. Hopefully that sort of clarified it. Whereas this is for when we've got a function inside another function. And remember what we said is ultimately you differentiate the outside scenario of the thing times by the derivative of the inner mechanism or inner function. Okay, and this is what we're going to clarify now. So for example, here, ultimately, big picture, if we zoom out sort of mentally, then what you've got going on, it's an e to the something, it's an exponential. Within that, though, the inner function is a linear function. So ultimately, an e to the something goes to an e to the something, and then I times by the derivative of the inside function, ax plus b. The derivative of ax plus b is just a, and that's what it would become. So here, if we look at this one here, big picture, this is a something to the power of n. Within that something was sine x. So ultimately, it's an x to the n, which would differentiate to n lots of that thing to the n minus 1. Within that, sine x, sorry, and then sine x, and then that differentiates to cos x. So the derivative here would be n, then it would be sine x to the n minus 1 times cos x. And that would be the chain rule for this. So can anyone tell me off the back of that, what would happen for these two questions here? If I had sine of ax plus b, how would that differentiate by the chain rule? Because big picture, the outermost function is sine, and inside that is a linear function, ax plus b. So if you were to differentiate sine of the thing, what would it go to? Times it by the derivative of the inside. So this is actually sort of a fairly basic chain rule, but could you guys let me know what you would get for that? So the outside scenario is sine of something, which would go to what? And then the inside function is ax plus b, which you're going to differentiate and times your other bit by that. So any suggestions? Brilliant answer. Sine would go to cos, so it'd go to cos of ax plus b, and then you'd have to times by the derivative of the inside bit, which would just be a. So a cos ax plus b. Superb. Thank you, guys. Excellent. What about the next bit? Be careful with this one. What would we get for this one? So cos, and some of you explain that really carefully. What would go to what, and then what we would do. What would we have here? Brilliant. Brilliant answers. Yeah. So cos would go to minus sine. And the derivative again of ax plus b is a. So minus a sine ax plus b. Super. So I think it's time to get onto some slightly trickier ones now, where again, we really think about what's the big picture, what's the outermost function, what's the innermost function. And I'm going to sort of suggest we maybe think of it like this. So big picture for this one, we've got a cos x, a cos of something. I'm going to put capital X to remind us it's of something else. That would go to minus sine of that something. Now within that, g of x is a cubic. Oh, what am I doing there? How would that innermost bit differentiate? Three x cubed minus 2 would differentiate to 9x, just 9x squared. Well done. So the times by the 3, 9, drop the power by 1, and the minus 2 goes. So putting this together, we have got to be careful, because you're going to have, that's it, excellent. You're going to have, what are we going to have here? The cos will go to minus sine. So we want g dash x times by f dash of g of x. So we're going to have 9x squared, this inside bit differentiated, times by minus sine of what was originally in there. I think that's a really good one to have done, because that really encapsulates all that's going on with the chain rule. Can you guys just give me a yes or no if that was clear? Because I think that's a really good way. If we understand that, we effectively do understand what's happening with the chain rule. Good, really good. Excellent, guys. Well done. Please do let me know if it needs clarified though. So this bit, this one here, looks awful, but again, let's break it down in the same way and feel free to work ahead of me. What's our outside function? What's our inside function? So ultimately, big picture, it's like an e to the x, isn't it? An e to the x differentiates to e to the x. E to the something differentiates to e to the something. I'm going to use a capital X. Now that something is actually, and I'm actually going to not write 1 over root x. I'm going to write x to the minus a half. Now that would differentiate times by the power, minus times minus is plus. Okay. Now putting this all together, I'm going to get that the derivative is 2x plus a half. Oh, well done. Some of you are there. Yeah, very good. Very good. Check you agree. Yeah. Very good. We happy with that? Well done if you got it. Is everyone good with that? Apologies, guys. I think the hay fever's kicking them. Keep sneezing. Are we good with that? Is everyone happy that I think that was a much, actually we're on to harder ones now, and it's perhaps easy, like some people are finding it easier to follow the process when there's more going on. So what we're going to do is we're going to do another big one like this. I'd love you to sort of take a minute to work ahead of me, and then we'll look at some exam questions as well and some other kind of final techniques to look over. So here's one for us to look at. That'll be great. I'll give you a minute or so to think. Feel free to share. I'm going to sort of just give you a moment to beat me to it. And I'll start writing out a suggested starting point. Okay. And let me know any sort of steps that we know. What's the outermost function and what's the innermost function? So the outside function here is sine, which differentiates to cos. Well done. Some of you have got there already. Well done. This one actually in itself is a chain rule. This is a bit harder because this is actually like e to the minus x plus 4x all to the half. So you've got to do like a chain rule within a chain rule. Brilliant. Thank you, Casey. I'll have a little check of that in a minute. That looks really good. So this will become, yeah, this bit's actually quite nasty. This becomes half e to the minus x plus 4x to the minus a half times by the derivative of the inside, which is actually minus e to the minus x plus 4. So that was quite a nasty derivative to do. Now, putting this all together, and I'm going to tidy it up. Does everyone get this bit? Because this in itself was a chain rule. So that was really quite nasty. And we can actually write this in a combined way here. Yeah, this was a bit of a mean one. or that is just the derivative of that. That's quite nasty. So putting this all together, we're going to get, which is quite hard to write in a chat, but do check you agree. Let me know if I need to clarify the fraction or anything. And feel free to screenshot. Let me know if that's clear. So that was actually a chain in a chain. Does that? Oh, okay, good question, Casey. Thank you for asking this. Are you talking about this bit here? How come you have to keep the... Okay. Because this was the root of e to the minus x plus 4x, that's like it to the power of a half. So that is a chain itself. So what's happened here, because this was significantly more difficult to the other ones we did, the halves come down and we drop the power to the minus a half, but you still have to times by the derivative of the inside. And the derivative of e to the minus x is minus e to the minus x, because that's, again, a little mini chain. E to the minus x, the derivative of minus x is minus 1. So that becomes minus e to the minus x. And the derivative of 4x is just 4. So what you're doing is you're doing times by the half, drop the power by 1, and then times by the derivative of this, which is actually this. So this is actually quite a horrible big chain rule itself. And that's just part of the ultimate problem. Yeah, great question. So that was a really good one to look at and do. Right, guys, give me a quick checkpoint, and then we're going to do some exam questions here that will really sort of show off how this could come up and give you a sense of how it would come up in an exam. So just go a 1, 2, or a 3 to let me know how you're getting on. Cool. Here we go. Thank you, guys. Yeah, no worries. Let me know if there's anything you want to go back over, clarify. Otherwise, we're gonna look at some exam questions, putting this all together. Here we go. So very much like what you'd see in an exam. The point P lies on the curve of equation y equals 4e to the 2x plus 1. The y coordinate of P is 8. Find in terms of ln2 the x coordinate of P. So this isn't sort of straight in there with differentiation. This is testing other things, which obviously with an exam is likely to happen. So how would we do this? Well, they've told us that y is 8. Do feel free to beat me to it with this one. So 8 is equal to 4e to the 2x plus 1. So let's try that. And then if we divide both sides by 4, take the natural log of both sides. So that means that x equals half of that, or ln2 minus 1 over 2. Is everyone happy with part A? Hopefully, yeah, excellent, Casey, well done. Now, just as a general exam technique reminder, soon as you see the word gradient, tangent, normal, perpendicular, parallel, that should be screaming out differentiation, derivative, rate of change, anything like that we need to differentiate. Because even if you think it's just big question or you're going to struggle with it, if they see that you've differentiated, they've actually seen you've recognized the skill that they're testing, and you will get method marks. So after part A, it says find the equation of the tangent. Well, tangents require a coordinate, which we now fully have. We have this dodgy looking coordinate, a half ln 2 minus 1, 8 as point P. And we also require a gradient. So we're going to need to do differentiation here, which we can do. So let's do that now. Part B, let's do the derivative, dy dx of this. Can anyone tell me what it is? So we're going to use chain rule. It's not too bad, actually, this one. How does this differentiate? So it's an e to the something, which will go to an e to the something, and then we times by the derivative of the inside function in the exponential. Brilliant. Excellent, Casey. I completely agree. This will differentiate to 8e to the 2x plus 1. So it is a real sort of simpler chain rule to the ones we've just been doing, but does everyone agree with that? This actually tidies up quite nice in a minute. Quite nicely, this one. Are we all happy with, agree with Casey there that the derivative for this would then be 8e to the 2x plus 1. So if I substitute x in, which is a bit of a random one, to find the gradient at that point, at the coordinate P, 8e to the 2 lots of a half ln 2 minus 1 plus 1 to the, that would just become ln 2. And that actually just becomes 8 times 2. Gradient is 16. So do clarify you're happy how I've subbed that in. What I've subbed in is I've subbed x into here. 2 times a half just gives you ln 2 minus 1, plus 1 just gives you ln 2. E and ln 2 cancel each other out, so it becomes 8 times 2. So 16. This is probably a really worthwhile one to have done. Subbing in a log into an exponential. And then the actual equation of the tangent, y minus y1 equals m x minus x1. And if you want to rearrange that into a y equals mx plus c form, you can, but that's actually done. Any questions there? Let me know if there's anything you want to check with that. Otherwise, we'll carry on with some more exam questions just so we're getting a flavour of how they're different as well. But I think that was a really good question to have looked at. So let's try the following. And I'm happy to go back or answer any questions as we go if you need. Let's look at this one. So a rock contains a radioactive substance which is decaying. The mass of the rock, m grams at time t years after initial observation, is given by m equals 400 plus 80e to the minus kt, where k is a positive constant. Given that the mass of the rock decreases by this much in the first 10 years, find the value of k. Now we do have to think carefully about what they've actually given us here. Okay, so we know some specifics. So we know at the initial time, don't forget, and this is a very common thing, is everyone happy that initially t is 0? So we could find out and work out the initial amount when t is 0. So when t is 0, what we would have is we'd have m equals, and some of you might have beat me to it, e to the 0 is 1. So that would come out as 480. So that must be the initial amount of grams. Does everyone agree with that? So you're just subbing in 0 as t. Yeah, excellent. Now t equals 10. Let's look at what's happening. So what we're going to sub in is we're going to say that if it decreases by 0.2%, then actually we know that it's equal to 0.998 times 480. Does everyone agree that it's equal to 99.8% of what it was? So that means that 400 plus 80e to the minus 10k must equal that number. So we can now rearrange that and solve it. So whatever this is, 400 and then if we divide both sides by 80, and then take logs of both sides, feel free to work ahead of me and find this. I believe what we're going to get is minus 10k equals ln so when we, yeah, that's it. No worries. Okay. So all of this, if anyone's missed anything, this is all sort of viewable after. That's no problem. So we're going to just try and finish this question off as we are quite near the end now. But there is a sort of final part where it links in with the derivative, which I think is really important to see. So very good. Well done if you got an equivalent answer. So then it says, given that the mass of the rock, yeah. So it says the rate at which the mass of the rock is decreasing when t is 100. So what we want to do now is we want to actually find the derivative dm dt. So if we differentiate this by chain rule, it's again quite a nice straightforward chain rule. What would this become? This is it, differentiation. So differentiating that would give us minus 80 k e to the minus kt. That's your little bit of chain rule. Does everyone see that? And now we actually know what k is. We can sub that in and we can sub t in as 100 and we can get the answer. Yeah. So we can go, we can sub in the previous value of k that we had, as well as the time we want, and we can use that to find the rate at that specific time, which is like finding the gradient at a specific point, just in a context. Very good if you got that as the derivative. So guys, we're very sort of, yes, exactly, and t subbed in as 100. So what we've done, just for those that have just joined or working through that fully throughout, either way, we've looked at the chain rule and we've broken it down sort of from scratch, built it up and looked at it as for functions within functions. So my biggest bit of advice when doing this is think, what's the big picture? What does that ultimately become? An exponential becomes an exponential times by the derivative of the inside function. That's how to sort of view it. And I like breaking it up with this f of x, f dash, g of x, g dash. And then just remember, it's not a product, it's a chain. It's a function within a function. But I think that was really, really good. And thank you so much to all the brilliant responses, answers, and questions throughout. If you want to revisit any of that, go back over it, please do. Good luck to anyone doing any exams this week as well. It's been a pleasure working with you. So really, really well done. That was great. So yes, so please do look out for more web classes on Sundays as well. Hopefully they're helpful. Really well done. Good luck with any mocks and any real exams as well. And thank you again for taking part. I'll let you guys go. Really well done. Keep well. Good luck with it all. And thank you for joining in this web class. Well done, guys. Take care. Thanks. Bye.